Welcome to Visual Algebra Lecture 0.1. What is Visual Algebra all about? I am Professor Macaulay, and I'm recording this in December 2024 as I'm starting to record a brand new Visual Algebra YouTube series. That will cover my forthcoming book, Visual Algebra, which has over 500 pictures and about 800 pages. This YouTube series will be about 100 lectures long and will cover more than a year of undergraduate algebra, though the first few chapters will be widely accessible, even to bright high school students. This material can be used for first semester graduate algebra as well. I've done it. And I will record an abridged version for that, which will be targeted for those people interested in visual algebra, but who have already taken an abstract algebra course. This is the first of two, well, so far I won't roll out more, introductory preface lectures. In this lecture, I'll give some background and history and explain how this differs from my popular visual group theory series, which is now almost 9 years old. Spoiler, there are a lot of differences, and I like this one better. For one, this will be more than twice as long and have a lot more content. I'll go over what's new. I'll also show you some sample exam problems to demonstrate the sort of questions that I can ask, which are often completely inaccessible in a traditional algebra class. I just have a bigger toolbox. I'll also answer a few questions, dispel a few myths about visual algebra, and show you some resources to learn more. In the second lecture, the one after this, called Highlights of Visual Algebra, I'll give you a whirlwind tour of about 50 visuals from all 11 chapters of my book, with light commentary. Many of these have never been seen before by anybody. Okay, let's get started. Here's a picture from the first section of the first chapter in my book, and also the first lecture, or lecture 1.1, in this YouTube series. I like to start with this. Most algebra books, they start with axioms, and then they give examples. Like, oh, here's a group, the integers, or the integers mod n, or the symmetries of a triangle, without much motivation. And of course, this makes sense for a mathematician teaching this, maybe who's an algebraist, but for a 19-year-old seeing this for the first time, or someone going to teach high school math, why are we doing this? And even if they get that, why not put a picture like this in the first few pages of your book anyways? I mean, this adds insight. You can see things like RF equals F R inverse. Now here are the symmetries of a triangle. And I like these two pictures because it really shows how different generating sets for the same group can give you very different looking Cayley graphs. And this group switchboard thing here, this is an analogy that I developed when I was teaching, trying to figure out how to explain group actions to undergraduates and not doing very well at it. And I really like this analogy so much that I put it in the very first chapter so students get used to it when we get to group actions. So the analogy is that you have a button for every element in the group. And when you press a button, these configurations move around. So when you press the R button, you follow the red arrows. This one goes here, this one goes here, etc. When you press the F button, you follow the blue arrows. This one goes here, this one goes here. When we press the R squared F button, then you do R, R, and then F. So the R button followed by the F button is the RF button. Now, let me just mention that these blue arrows over here and the green arrows are the same, or at least these blue arrows are the same as these blue arrows. I start by making them double-sided, and then I say, you don't need double arrowheads. If you have double arrowheads, just drop them and make it like this. Okay, so this is how I introduce groups right away, and you can imagine what would happen if you had maybe instead of these triangles here, you had triangles with zeros and ones on them. So you have the all zeros triangle or the all ones triangle. So now you might have orbits of different sizes, and this switchboard analogy is really useful. Okay, I'm getting a little far ahead of myself. Let's move on. Now I want to give you a brief but wildly incomplete history of visual algebra with my own implicit biases and blind spots. In 1964, Grossman and Magnus published a book called Groups and Their Graphs, which, as far as I know, is the first algebra book that heavily uses Cayley graphs. That's been recently republished by the MAA, so you can find it, and it's not too expensive either. In 2000, around the year 2000, give or take, Doug Hofstetler at Indiana University went on sabbatical and developed a course he called Visual Group Theory and Galois Theory. And he was heavily inspired by this book here. Now, if you know the name Doug Hofstetler, you recognize it. He is the award-winning author, Pulitzer Prize winner, of Gödel, Escher, Bach, which is a cult classic book, at least when I was in college in the late 90s and early 2000s. Everyone had it, everyone read it or read parts of it and quoted it. Talking to my students now, they don't seem to really know it very well. Many had not heard of it, so it seems like it's going out of style, and I hope it doesn't, or I hope it makes a comeback like the TV show Friends and things like that. But I encourage you to check it out. Get yourself a copy. I think it's from like the 1970s. It's an old book, but it's a great one. So he was at Indiana when this all happened, and I think he taught this course 3 times. And one of those times, Nathan Carter was a PhD student who took the course, and he got an assistant professorship at Bentley University in Boston a couple years later, and he published a book, Visual Group Theory, when they're basically on the course. And I met him at MathFest in 2019. A year before, I first taught modern algebra at Clemson University, and I decided to use his book. Now, his book is a general audience book. Stephen Strogatz at Cornell calls it one of the best introductions to group theory or to any branch of higher math I've ever read. And that's a great assessment, but emphasize introduction. It's general audience, so it's not appropriate. It's not quite at the level of undergraduate math majors. So I had to massively supplement it. For example, I think there's only one isomorphism theorem in there, and it's intentionally written to do everything from a visual perspective rather than a formal logic base. So I had to add all that stuff as well. So as I supplemented this and developed those slides, I ended up recording 43 lectures on this course, and that's on YouTube in 2016. And that's a course, it's gone viral. A couple of those lectures have gone viral a few times on like Reddit Math and I think Hacker News. And so I know as of this recording, the first video has like 180,000 views. So many of you likely know of that. I've gotten comments and emails about that. And this lecture series is a new and improved version. I think it's a very much improved version, which is ironic because at the time I thought this is how my course had converged to, and I'm never going to want to really change it. I think it's good the way it is. But that changed when I started writing Visual Algebra in 2019 and discovered all of these examples and came up with new visuals and new content. And I'm like, wow, this is a better way to do things. So while I still like this video series, I highly recommend the one that I'm doing right now. Now, in between this time, 2016, Dana Ernst at Northern Arizona University, who introduced me to Nathan Carter at MathFest in 2009, is a co-author of mine. He wrote an inquiry-based approach to abstract algebra, which you can't tell from the title, but is a visual algebra textbook. And it uses the inquiry-based learning method, which is kind of self-discovery. So it doesn't include the proofs. The students are supposed to provide them themselves. But this is freely available on his website. I highly recommend checking it out. So once again, I started writing Visual Algebra in 2019, having really not any idea where it was going. I certainly did not think it would be 800 pages and 11 chapters with 500 visuals. But I soon realized, especially when writing this book, I'm going to have to record a new Visual Algebra YouTube series. I don't want people reading my book and relying on this old series, even though that's not bad. But also, I really want to showcase what I have, what I've done for everyone out there, even if you don't own my book. I want people to be able to self-study. I think there's a lot of value in that. Not everybody has the discipline to take 800 pages and go through it, etc. It's nice to watch YouTube series. I watch YouTube series. There's some really good ones. If I want to learn something, I think it's more effective than reading a book because I can pause things, I can rewind it, etc. And it's broken up into chunks where you can actually get through things rather than a book. You can get stuck on a page, and you know what that's like. So that's what this is about. And in the rest of this lecture, I'm going to tell you more about that. So first of all, one big change. This is where I'm sitting right now. I have a new Visual Algebra recording studio. My old lecture series, I used an iPad from 2016, I think, maybe 2015. And I think I had a cheap headphone that, the sort of headphones that people use in like call centers. It's not nothing, but it's not a professional grade equipment. And now I did buy a very nice mic, and I forget what the synthesizer, whatever they call these things. And it sounds a lot better. I mean, I've listened to my own videos, and I can definitely tell the improvement in quality, at least purely from an audio perspective. Okay, let's actually compare these two playlists side by side. My Visual Group Theory 1 from early 2016, 43 lectures, and it covered one semester of undergraduate algebra following Nathan Carter's book, but I really had to massively supplement it, as I mentioned. My Visual Algebra series that I'm making right now, I'm saying 2025 because the vast majority of it will be recorded then, is going to be about 100 lectures. It will cover more than 2 semesters of undergraduate algebra. And I have taught a whole year of undergraduate algebra, and I have not gotten through everything. Or I guess I have sort of gotten through stuff, but I've had to really rush and summarize a chapter. So it's more than a year of undergrad abstract algebra, and I really pack my courses. So when I say a year, it really is probably 3 semesters worth. Alternatively, the content of my book, I teach with graduate algebra. Now, I do a very abridged version of the first 4 chapters. I mean, in my undergraduate class, my first 4 chapters, I think I spend 10 weeks on out of 15. In my graduate class, I think I spend 3 weeks plus 1 day, so like 3 1/3. So that's it's a massive difference. Like in graduate algebra, I don't go through how to compose permutations. I don't remind you how to do 1-to-1 and onto. There's things like this that I just don't do in the graduate version that I do in the undergrad version. So and if you have taken abstract algebra, you will find my first few chapters of this series to be a bit of a slog. Like, I think I have 3.5 hours of groups intuitively, which is really nice, but you might not need all of that. So what I will be doing is I will be recording a graduate visual algebra series targeted for people like you, where I go through those first 4 chapters really quickly, where I assume that you know what groups are and you just want to get up to speed as to how to do the visuals, and also maybe refreshing some of the main proofs as well. I'm not going to skip those proofs in a graduate course. Even in any graduate course, they still prove the isomorphism theorems and things like that. Okay, so here's a list of terms that are original, at least in their meaning, to my book and video series. So the group switchboard I already told you about. Blue and red cosets. That's a very nice mnemonic that I think is very effective. Shoebox diagrams, I'll talk about those, and we'll do the isomorphism theorems. Pizza diagrams. This actually is due to Doug Hofstetler. Semi-abelian groups. Now, this term exists, but it does not in the literature. If you Google it, it will come up. But specifically, I have something I call the semi-abelian group, which doesn't clash with multiple independent definitions of this, but I really think is a good name. Diquaternion group is a group that, as far as I know, a family of groups that doesn't really have another name. And so I came up with this one, and it really is like adding a dihedral group to the quaternion group. And I have a monthly article that I published in 2024 about dihedralizing the quaternions, and I encourage you to check that out if you're curious. Moderately unnormal and fully unnormal subgroups, moderately uncentral and fully uncentral elements, G-set posets. G-set is a very standard thing. Concept that a lot of people, you can talk to algebraists, people who teach algebra, don't even know what a G-set is, at least from that name. It's something it's a group action with a set. So people say, why even define that? But I will convince you that this is something that you need to define, and then you can have a poset of a bunch of G-sets. Maximal central ascents, maximal central descents. This has to do with how you define nilpotent groups and ascending and descending central series. maybe someone's done this. I've never really seen it, but I think it's a really nice way to do it in terms of universal properties that has a very nice visual component, especially in this course, we're going to really rely on subgroup lattices, and we'll get to know a whole bunch of them. And that it'll be an incredibly useful toolbox where we can use techniques involving central ascents and descents that if we didn't have lattices, we couldn't really do that. The crooked ladder theorem is how I proved that the ascending and descending central series have the same length. And I use something called, well, you can imagine what a subring lattice is, but I annotate it with colors to represent different subring structures in a unique way. And then when we get to chapter 9, we do some algebraic number theory. I'm going to construct lattices involving the ideal class group. And I'm not a number theorist. I don't know too much about it, but I've showed this stuff to number theorists. And from what I can tell, they say, yeah, I haven't really seen this before. So that's what's new in this book. And there's probably a lot more. It's hard to come up with a list. This is all that fit. And these are really, I think, the bigger ones. Here's the table of contents. And I want to say a few words about this. First of all, the organization of this book really just kind of came together organically. This is the way that it's most natural. The first chapter is on groups intuitively. I give examples of symmetries, of polygons, of friezes and wallpapers and crystals. I talk about puzzles like the Rubik's Cube and others. Talk about group presentations and Cayley tables. And then I end with some examples, some potentially troubling examples of things that look like Cayley tables, but don't describe a group. Things that look like Cayley graphs, but don't describe a group, which really hits home the idea of why we need a formal mathematical definition. We cannot just use the visuals to develop group theory. Now, I did not even know of these examples in 2016 or 2019 for that matter. And I'm pretty sure that visual group theory author Nathan Carter and Doug Hofstadter didn't know either. I'm pretty sure that most algebra instructors in this country do not know of these examples. Because if you're not going to use Cayley graphs regularly, you probably aren't going to come across them. And even if you do, you're probably not going to come across them either. So it's one of those sort of niches of math that most people don't know about, but is really important and insightful. So that's chapter 1. Chapter 2, examples of groups. I go over all the standard ones, the cyclic, dihedral, abelian groups, the symmetric groups, the alternating groups. But then I do a lot of non-standard ones. Dicyclic, generalized quaternion groups, diquaternion groups, semi-dihedral, semi-abelian groups. These groups, a lot of people have not heard of. In fact, some of you haven't heard of because I made up their names, or one of them I made up the name, and another one my student made up the name. And they're not common because they have these unmotivated presentations that are really just not insightful. But once you see a Cayley graph, which is really just a presentation visualized, the structure comes to life. When you see their subgroup lattices, they have different structure from the other examples. And this structure is rich and it's deep. And it provides insight that the other groups do not. And so it's so crucial to have these examples at hand as you go through this course. And I've had students tell me when they get to graduate algebra, like in a different university or a different professor, that it was really helpful to have those examples as they went through a traditional graduate algebra course. And that right there is one reason why I think it is so important, why it's so helpful to have this pedagogy as an undergraduate before you go to grad school. Some people think it's just for people who are going to teach high school. No, it's really helpful for people who are going to graduate school in mathematics. Chapter 3, this is on group structure. This is on things like subgroups, subgroup lattices, cosets, normal subgroups, normalizers, conjugacy classes, both of elements and of subgroups. I talk about direct products and I talk about quotients. I should say semi-direct products comes up in chapter 4, but I give a preview in chapter 2. I talk about how to construct them with this sort of inflation method and twisting method of Cayley graphs. Because semi-direct products are great examples that come up in chapter 3 and 4 as well. And I think it's important to see them early so we can talk about them and to get some intuition of what's coming next. So we talk about semi-direct products in the chapter 4, maps between groups. That's when we formalize it. Before then, we talk about homomorphisms and the isomorphism theorems, which I do in a different order than most people. I will hopefully convince you why my order is the most natural. See if you are convinced. We also talk about automorphisms, both inner and outer, and other topics like not just semi-direct products, but central products. Okay, actions of groups. This I do very differently, I think, than a lot of people. First of all, I use right actions because I wrote this book and this course using right Cayley graphs, where you read left to right. And you really have to stick with one of those, or pick one of those and stick with it. So I picked right actions, and now it's too late to change, but there's a good reason. I can make a case for why that is, why the pros of that at least match the cons. Okay, so I talk about G-sets, which is just a group with an algebraic structure on it. It's a set with an algebraic structure, and a group is like a special case where the G-set has a binary operation. So I think that's really important because we can talk about, because later on in this chapter, I talk about homomorphisms of G-sets and equivariance, and anyone who has taken an algebraic topology course and studied covering spaces and deck transformations knows that the deck transformations, that is equivariance of G-sets. They don't talk about it then, but I know that I would have done a lot better in my algebraic topology course if I had fully understood my chapter 5 of actions of groups, especially with G-sets. Okay, so other things, I do the seal of theory in there as well. Chapter 6, extensions of groups. This is something that I think one of my complaints about a lot of algebra courses is they just don't do extensions well. They don't emphasize what it is, and really solvable groups, nilpotent groups, and composition series and Jordan Holder, all of those are about extensions, but they're different kinds of extensions. So I could say more about this, and I will say more about this in my next lecture when I give that highlights of visual algebra. There's not much more I can say without pictures, but I think the way I do chapter 6, I really like it. I think it, most books, there really is strong connections between composition series, derived series, and the upper and lower central series that really most books just kind of miss. They throw them out there in some random order, sometimes in different chapters, and it doesn't really tie them together. I like to ask people who teach graduate algebra, explain to me in a minute the difference between solvable groups and nilpotent groups and what that's all about. And I really don't get any good answers. And I think after watching my chapter 6, I think you can give a very good 2-minute elevator talk about what those things are all about. Okay, chapter 7, universal constructions, things like commutative diagrams, maps factoring through. It kind of ties together a lot of the previous stuff and also introduces motivates a lot of the later stuff. We do we do products and co-products. We do free groups. We do free products. We formalize what a group presentation is. We talk commutator subgroups, nilpotent groups. We all put that in that context. Then I do chapter 8 in rings. Chapter 9 is domains. I could say more about this. Again, I'll show you I'll say more in my next lecture when I show you pictures. And then fields and Galois theory, this is the most recent one. I think that's fairly self-explanatory. In terms of undergraduate algebra, what I teach, I go through the first 5 chapters of this, and then I do some rings because I need to fit some rings in that course. And then for the second semester, so I've taught undergraduate algebra a lot. I've only taught algebra 2 once. It really hasn't been offered a bunch at my university. When I did that, I went back and I did the second half. Actually, I think I did all of chapter 8. Again, I did chapters 6 and 7, and then I briefly summarized chapters. I had not written chapters 10 and 11 at the time, but I quickly summarized Galois theory. I needed more time to do it. So some of the proofs I didn't do, but basically, the union of what I did was this entire course with some of the stuff kind of rushed through and summarized. So I teach a lot of content in my undergraduate algebra course, and I don't think I can get through all of this properly in 2 semesters. I can get close, but that should give you an idea as to how much content there is. Again, in graduate algebra, I do the first 9 chapters. As I said earlier, the first 4 chapters I do in 3 weeks and 3 1/3 weeks in graduate algebra, but I do it in like 9.5 weeks, I think, in undergraduate algebra. So that's the difference. I can get through stuff a lot quicker, and I have a whole different set of slides if you come in knowing what a group is and some familiarity with it. And then again, I go through all this stuff. Fields and Galois theory and modules are all done in Algebra 2 at the graduate level. So this is 1 semester of graduate algebra. Book does not cover a whole year because it doesn't have anything about modules at all. Maybe one day I'll write another book or a second edition, but that won't be for some time. Here are some new topics that I cover in visual algebra, and hence in this YouTube series, that I do not cover in my 43 lecture visual algebra YouTube series. And there's a lot of content here. So semi-direct products, I did not do at all. Central products, Cayley graphs on polytopes. The symmetric and alternating groups a lot of them can be built on polytopes. Free and transitive G-sets, or just G-sets in general, I don't mention. Fixitors and group actions. The orbit counting theorem, or the Burnside's lemma. Inner and outer automorphisms. Action equivalence and equivariance. Group extensions. AN being simple. I don't think I included proof of that. Short exact sequences. Composition series, the Jordan-Holder project. Compositions, I guess I had that one. Maybe I should cross that one out. Nilpotent groups, universal properties, basic category theory, products and coproducts, free groups, free products, formalizing group presentations, Zorn's lemma, primary ideals, nil and Jacobian radicals, rings and fields of fractions, the ideal class group, an algebraic number theory, the Chinese or Sun-Tzu remainder theorem, Hilbert's basis theorem, cyclotomic polynomials, separable field extensions, transitive groups, Galois theory proofs. I do a Galois theory chapter in my visual algebra or my visual group theory playlist, but I don't do really the main proofs. It's something that I do in the last couple of weeks of my class. I want to give them the idea for how it works, but I just don't have time for the proofs. Symmetric polynomials, and also the Galois group mod P reduction. So this is a lot of content. And again, this is stuff that's missing from visual group theory because that was a 1 semester undergraduate course. And I don't think I had it streamlined in such a way that I think I cover more content now. I'm more efficient with it. So, if you're asking which course should I take, for most of you, or which series should I watch? Most of you, I think that's going to be visual algebra. Here's something else new in visual algebra. I heavily utilize the LMFDB. This is, what does it stand for? L series of modular forms database. This is put together by some number theorists, but they also have a group database. And this is fantastic. Like, here's a screenshot of it. You can search groups by order. You can put all these parameters and find the list of all groups of order 32 that have, that are non-abelian and have so-and-so as their commutator subgroup and so forth. And these groups also have subgroup lattices that you can visualize built in and a whole bunch of statistics. So if you click through groups. So I encourage you to check this out. I rely on this a lot in my course. Maybe not as much in the YouTube series, but I will mention it from time to time. And I encourage you to check it out. Now I want to go over some visual algebra myths. So some people, when they hear visual, they think easy or less rigorous, etc. So myth number 1, a visual algebra course is less rigorous than a traditional algebra course. That is, at least for mine, completely false. You can teach a visual algebra course that is not as rigorous. Nathan Carter's book is not meant to be fully mathematically rigorous. It's meant to do everything visually. If you teach a course out of that, yes, it would be less rigorous. But inherently, it is not true that this visual algebra course is any less rigorous than a traditional algebra course. Myth number 2, a visual algebra course is easier than a traditional algebra course. This is entirely false. Again, people see visual, they think, oh, it might be easy. I'm pretty sure that my current algebra course, this YouTube series, is definitely harder than if I were to teach a traditional algebra course. In fact, I got an email last month, I'm reading it right now, from an undergraduate at my institution saying, I wanted to reach out and thank you for making your notes for algebra public on your website. I am enrolled in algebra right now, and I found yours to be much more difficult, parentheses, and hence fun. This is someone who's very strong in math and probably going to grad school. And he's like, yeah, your visual algebra course is harder than the one I'm taking right now. Doesn't have to be. Again, you could teach an easier one if you wanted to. And actually, I would say that you probably can. It's easier to teach an easier course if you want to visually, but it certainly does not have to be. Myth number 3, a visual algebra course just amounts to supplementing existing material with visuals. This is also false. And in the next couple slides, I'm going to convince you of this by showing you several problems from my exam and the questions that I can ask that you cannot ask in a traditional algebra course. Now, if you haven't taken abstract algebra, you are not going to follow these exam questions. But again, that's why I'm putting it near the end of this lecture. Myth number 4, the visual pedagogy is primarily targeted to students not going to grad school. I got this feedback when I submitted a draft of my book. Someone said, I think this is probably meant for people not going to grad school. And that is so incredibly false. Now, I had only submitted a couple introductory chapters, and so they had not seen my chapter 4, my chapter 5, my chapter 6, which is really rigorous. So that's partially on me, but also that was not a deal breaker. The editor wanted to publish it anyway, so that was just a comment from, and I suspect that maybe they just looked at the first chapter. And yes, the first chapter, if you're only going to do that, is targeted toward a wide audience, and especially, I think, great for people who maybe are teaching high school mathematics. But this is absolutely false if you look at the whole content of this book. Myth number 5, students who don't learn visually won't enjoy or do well in a visual algebra course. I think this is entirely false because, again, this is not an alternative way of learning it. This is a supplement. This is a whole new toolbox and skill set which involves, subgroup lattices. But at its core, again, it's not an alternative to the regular pedagogy. It is in addition. And if I can show you the next couple slides with exam problems, I think I can convince you of that. And finally, myth number 6, what I hear from my colleagues, people with PhDs in mathematics who teach abstract algebra, they say, teaching a visual algebra class would just be too difficult, or I wouldn't know how to do it or how to start. And I get that, because if you've never done it before, you don't know where to start. But, I have materials available. I have these YouTube lectures. Maybe you don't want to watch them all. I have all of my materials on my course website. I have all of my slides that are very well curated and I've used many times and have refined down to something that I think is very nice right now. I have all of my homework assignments and LaTeX files posted. I have all of my exams posted. Feel free to use any of that. Feel free to reach out, send me an email, ask questions. When I wrote this book, I was on the fence. It's like, do I want to just do things how I did before, or do I want to just rip up and do it again, start from scratch and do my course? And I finally did that, and I am so glad that I did. It's so worth it. It's so much fun. But I get it. Like, I have not taught intro to proofs. I have not taught combinatorics. These are courses I know pretty well, but I'm not really sure how I would teach those things. I mean, it's a blank slate. So it's always a blank slate when you do something new, even if you know the material somewhat well. At this point, we have 5 slides left. The very end, we have a welcome slide with links and resources. Before that, we have a picture to whet your appetite. And then we have 3 slides that are like this. These are exam questions that I wrote myself. They're all original. This one is from my spring 2024 final exam for undergraduate algebra. And I just want to show you what it looks like to work through these and solve these. I'm going to go at a kind of fast pace. I don't expect everyone to follow, but imagine you're looking in just to I want to give you a flavor for what sort of things we can do. And this is not instead of traditional algebra. I have a lot of questions that are traditional algebra proofs. Any sort of thing that we do in a traditional algebra course, we can do in my course. We cover that stuff. Okay, so this is the semi-dihedral group, ST8, and the subgroup R squared. See, that's right here. That has order 4. That is isomorphic to C4. And G mod that, let's see, so you go above this, and that is this Klein 4 group. So that's going to be V4. The subgroup generated by R to the 4th, where is that? That's right here. That's isomorphic to C2, because that's got order 2. And the quotient, this group right here, is the dihedral group D4. G has 3 order 8 subgroups. This one is isomorphic to, so going down here, that's order 8. That looks like the dihedral group. That's D4. Generated by R, that looks like a cyclic group of order 8. That's C8. And then this one here, you've got this little kite shape. That's the quaternion group. My students should know this by inspection. Find all ways that G can be written as a direct or semi-direct product of 2 of its proper subgroups. So we are going to look at ordered pairs of, so let's see, there is this and this. Those groups, they intersect trivially and they generate the whole group. So we have Q8, semi-direct product C2. And we also, I guess we have this one and that one as well. So if we do this one and that one, that's going to be C8, semi-direct product C2. Okay, partition the subgroups into conjugate classes by circling them on the lattice. That's normal because it's a unicorn. Oh, that's a term in my book that I don't mention anywhere. Yeah, a unicorn. I'll tell you about it later. So I should probably erase. This stuff. So what do we have? We have, those are order 2, so they're normal. Now this mod, that's a dihedral group. We know that the conjugate classes, that those are conjugate and those are conjugate in a quotient up here. So now we have, what about these? Are these all, let's see, if these are conjugate, then these two things have to be conjugate. I think all 4 of these are going to be conjugate because, yeah, S is conjugate to R4. Let's see. So conjugate, what's RS, R inverse? That's going to be RS, R inverse. Okay, so what do we have? We have this is conjugate to this, and similarly that will be conjugate. So all 4 of these are going to be conjugate. Okay, so I did this one. The normalizer of this conjugate class is size 4. The normalizer is going to have index 4, so that's going to be this one. So the normalizer of that one has to be R to the 4th. That's just orbit stabilizer theorem. And then the quotient of this, that's just C2. So the center of this group is, let's see, R to the 4th, red, 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 blue commutes with blue, red, 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 red. Yeah, so that's central. I don't think anything else is, nothing else, that's not going to be central. So the center of the group is generated by R squared, and its inner automorphism group is G mod the center, R to the 4th. And its inner automorphism group is G mod the center, which is D4. You can see that by inspection up here. The commutator subgroup, let's see, how far can you go down? So the quotient is abelian. That's by inspection, that's this. So that's going to be R squared, and the abelianization, you can see by inspection, it's V4. The generator S is conjugate to exactly how many elements? Well, it's going to be 4 because all of these order 2 generators have to be conjugate. So 4 elements, and the centralizer is going to have index 4, so that's also going to be R to the 4th. S is G a simple group? No, because it has normal subgroups right here. You can see it right here. So exactly how many of the 15 subgroups have normalizer equal to G? What I'm asking you is, what's normal? 1, 2, 3, 4, 5, 6, 7. So 7 of those have normalizer equal to G, and of them, and how many of them have normalizer trivial? Nothing has trivial normalizer. The normalizer has to grow, and this is a normalizer of H contains H, and normalizer of 1 is G. So that's going to be 0. Here's a problem from the final exam of my graduate class in the fall of 2023. It's a subgroup lattice that they've never seen before of a group of order 32. G mod C4 cross C2, that subgroup lattice, you should recognize as V4. And G mod C8, when it's defined, you know, if C8's not normal, like over here it won't be, but here that will be C4. The quotients of G by its 3 order 4 subgroups, reading from left to right. G mod C4, that I recognize that as D4. G mod V4, that's the kite shape is the quaternion group Q8. And G mod C4 over here, that is C4 cross C2. The commutator subgroup is, let's see, so, you know, this one we just said has an abelian quotient. So this is definitely, this mod that is not abelian. So that's C4 or semi-direct product C4. So C4 has to be the commutator subgroup, and the abelianization has to be C4 cross C2. So how far can you go down? So the quotient is abelian. That's as far as you can go down. The center of G trivially must be contained in the center of all of its subgroups. So the center of SA8 has order 4, and its quotient is V4. So for this, that has to be that C4. And for this one, it also has to be that V4. So that center, circle this group on the subgroup lattice. So yes, this is, I'm going to circle that right there. So the center of G must be contained in this. So it's either this, this, or this. I'm actually not sure which one it is. Consider the descending central series. Determine what the order 4 subgroup is with justification. So you start up here. You have to go down here because that's the next term. So this is L0. This is L1, and then it's now possible to determine the ascending and descending central series by inspection. So let's keep going. So L2 is how far can you go down where this is central? Well, you can't go down here because this will not be central because the center is contained in here. So this cannot be L2. L2 has to be this thing right here, which means this has to be L3. This is a nilpotent group because this is a P group. So this is the descending central series by inspection. The ascending central series, what do we know? We know that it has length 3. So the first step is the center. So the center is contained in here. It's got to be at least here because of this fact. So which one of these is it? Let's see, this thing is central in both of these, and this is abelian. So this thing here is central in all of these, so it's going to be central in the entire group because this group is, so this is going to be Z2. Sorry, this is going to be, so this is Z1, this is Z0, Z0, this is Z2, and this is Z3. So there's the ascending central series. For each non-normal subgroup, circle its conjugacy class. Well, this is the quotient is dihedral, so I'm going to circle those, and that's it. Everything else is, and these are not central, so they cannot be normal, and they have to be conjugate to themselves. So everything else is normal. These are the size 2 conjugacy classes. What is the inner automorphism group? That's G mod the center. That's D4. So that's D4 because it's G mod the center. Is G the semidirect product of any of its proper subgroups? Why or why not? Well, any two proper subgroups, let's see, any two up here, so you need two that intersect trivially. And so anything up here intersects in C2. So you have to have a C2 with something of order 16. But any of these, but this is contained in all those three, so there's no way that any two of these things are going to intersect trivially. So no, this is not the semidirect product of any of its subgroups. Here is the last example problem that I'm going to do for you. This one is for my undergraduate final exam in spring 2024. Again, it's online if you want to check it out. It's all the same except for I think the formatting I've changed to fit the screen. So the Galois group, they don't have to know what this is. They have not seen this. It's just an example of a group action that I'm showing. It acts on the set of 8 roots, which are shown right here. So this action has one orbit, a connected component. That's what an orbit is. And it is transitive. That means it's all connected. The orbit containing alpha naught has size 8. Again, do they know what this is? And the stabilizer is generated by S because it has order 2, because orbit stabilizer has order 16, size says 8, and there's your stabilizer. The orbit containing alpha 1 has size also 8, again, not a trick question. And stabilizer is generated by r squared s. We're looking for loops, so r squared s. Stabilizer of alpha 2 is s, so that's r to the 4th s. And stabilizer of alpha 3, I'm pretty sure is going to be r to the 6th s. Let's check it out. 1, 2, 3, 4, 5, 6 s, yes. So that's r to the 6th s. The automorphism group of S as a G set is isomorphic to the normalizer of H mod H. So what is, that's the stabilizer of any element. So we take S, we take the normalizer of this, and I think 2 problems ago was from the same exam. It was a different problem on this group, and so that problem they did that the normalizer of this group. So this had conjugate class at size 4, so the normalizer has index 4. So if this thing here is H, this thing here is the normalizer of H. So C2, this symmetry group this has C2 symmetry, and you can see that a 180 rotation is a symmetry. That's why it's 8. It's the normalizer mod H. Again, it comes up in deck transformations and topology. By inspection, we can compute the fixators of the following. The fixators of 1, so what is fixed by 1? Everything. What is fixed by S? We could just see alpha S or alpha 0, alpha 4. Those are the things that have the little blue loop. That's fixed by S. What's fixed by RS? So what is fixed by R? I don't think anything is fixed by RS. Yeah, because that's not conjugate to S. So empty set. What's fixed by r squared s? I think we already said that, so that's going to be where was it up here? Alpha 1, r s. So there's alpha 1, and I think there's going to be one more. I think it's going to be alpha 5, and alpha 5. The kernel of this action is the intersection of all the stabilizers. And the stabilizers are all right here, so the intersection is trivial. So that's going to be, the kernel is trivial. The set of fixed points is empty because there's all connected. There's no size 1 components. The subgroup, not a trick question. The subgroup here has order 2 because I'm making sure they're honest, making sure that they know this. And it has index 8. And this group is at order 16. So this subgroup has 8 cosets, 8 right cosets and 8 left cosets. I put every left coset, right coset has the same size. I'm making sure that we're on the right page. Let this group act on the right cosets by right multiplication. Draw the action graph. That's what this is. This is the action graph. So, if I want to draw this, I would say that this is H. This is HR. This is HR squared. HR cubed, HR to the 4th, HR to the 5th, HR to the 6th, HR to the 7th. And then the idea is it's going to be it's basically this graph, but you label these with HR to the I instead of alpha I. That's the idea is that this has the same structure as a graph of cosets. So do I need to do this? I think you get the idea. So again, this is, They do proofs in these exams, standard proofs, but they also do this stuff to make sure that they understand the concepts. And I think this stuff is at least as hard as the proofs. Okay, here's another example of something that is in my book. This was inspired from a picture from Nathan Carter's visual group theory. It's just showing how the integers mod 12 can be constructed as a quotient via the first isomorphism theorem. And finally, thank you for making it this far. Where to learn more? Subscribe to my YouTube channel. Follow me I'm currently on Blue Sky and Twitter/X. I'm mostly posting on Blue Sky as of December 2024, but things change quickly. This is my handle. I will post my slides publicly, all my course materials, my homework and my exams, and my LaTeX files for homework and exams if you want to use any of them. Currently, here's the website. That could change. I might buy a domain name, probably won't. This works for now. You can always use the Wayback Machine if it doesn't, or just use Google. You can find me. Read my articles. I have I mentioned this, a monthly publication on dihedralizing the quaternions and a Math Magazine article that is in press. It should be published in 2025 on Cayley tables and lattices of finite rings. Check out Nathan Carter's visual group theory book. Check out Dana Ernst's free open source inquiry-based learning book. Here's the URL. You can Google this. I couldn't fit the URL in here. Future to-do list. As of now, December 2024. Who knows? You might be listening to this 10 years in the future or more. Finalize Visual Algebra and publish it. I've written it, but I have to go through in detail, and I've made changes, and it's hard to go through an 800-page book. It takes a lot of time to check every little detail. Finish recording Visual Algebra. I have about 100 lectures. I've done about 10. I actually went through halfway through chapter 2 before doing this one. And graduate Visual Algebra playlists, put them on YouTube. And also, I will put LaTeX files for my slides on GitHub once my book is published. That's something I do not want to do that before publication for copyright reasons, but I will absolutely make my slides are available on here. I will make the LaTeX available as well, so you can use them in your own classes or for your own projects. Feel free to get in touch. Email is the best way. Sometimes if I don't write back, send me a nudge. Sometimes if it takes a thoughtful response, like a paragraph or two, I put that aside and then I forget about it because I'll do it in the evening, etc. Don't hesitate to send me a nudge. And thank you for listening this far. I hope you enjoy this YouTube series, and I hope you enjoy my book and my resources. And don't forget that coming up next is a video on highlights of Visual Algebra, where I'll show you about 50 slides with really fun and original pictures from my book with very brief commentary. I hope you stick around. See you then.